Hello, so for this lab we're going to do a redox titration reacting potassium permanganate, although the potassium is a spectator ion, with hydrogen peroxide. So this is a redox reaction. The first thing you want to do is balance this using the half reaction method. In reality, on the AP exam, you're probably not going to get a redox reaction to balance that is this complex, but it is good practice. So let's kind of walk through those steps. The first thing you want to do is split it into the two half reactions, the MnO4 negative, the permanganate, going to the Mn2 plus, the H2O2, the hydrogen peroxide, going into O2 gas. When you're doing this, you always want to balance anything that's not hydrogen or oxygen first. So manganese is balanced and there's nothing else there, so that's good. The next thing we want to balance is oxygen by using water. So because there are 4 oxygen atoms here, I need to use 4 water molecules to balance out oxygen. And then the oxygen is already balanced on this side. The next thing you want to balance are the hydrogen ions. And we do that by adding, we balance hydrogen atoms by using hydrogen ions. There are 8 hydrogen ions here, so I will add 8 hydrogen ions here. And then 2 hydrogens, so 2 hydrogen ions on this side. Last but not least, you need to balance the electrons. Balance the charge using electrons. On this side, I have an overall charge of +7, 8 from the hydrogens and a -1 from the permanganate. And on this side, I have a +2 charge. Now, the difference between that is 5. So what I need to do is add 5 electrons, and those 5 negative charges will bring this down to +2, and so our charges are now balanced. So now I have the electrons balanced for this one. For the other half reaction, I have a +2 charge on this side and a 0 charge on the reactant side. So I need to use 2 electrons for this one. Our next step is to make the electrons match. So 5 and 2, the least common multiple is 10. I need to multiply this whole reaction by 2. So I will have 10 electrons, 16 hydrogen ions, and 2 permanganates, going to 2 Mn2 plus and 8 waters. For my other half reaction, I need to multiply by 5. So 5 H2O2 goes to 5 O2 plus 10 hydrogen ions plus 2 electrons. Plus 10 electrons. And then you need to put the 2 half reactions together. So the electrons, of course, will cancel reactants and products. And then some of the hydrogen ions cancel. I have 16 and 10. So 10 of them will cancel out, and this will go down to 6. And I believe that's the only thing that balances, or that crosses out. So if we put all of the reactants, I have 2 MnO4, 5 H2O2, and 6 hydrogen ions. Turns into 2 Mn2 plus, and 5 oxygen gas, and 8 waters. So this is my overall balanced equation. The really important part about this is getting the mole ratio of the MnO4 minus to the hydrogen peroxide. It's a 2:5 ratio. And for this lab, the hydrogen peroxide is going to be our limiting reactant. So I need to make sure that I have a great excess of hydrogen ions, and we're going to titrate it with the potassium permanganate of a known concentration. We're going to use 0.02 molar potassium permanganate to react with our hydrogen peroxide and titrate it so we can find out the concentration of hydrogen peroxide present in a drugstore bottle, or in my case, a grocery store bottle of hydrogen peroxide. So let's talk about the procedure for this lab. First, have students prepare the burette. They should clean it with deionized water, then rinse it with the potassium permanganate titrant, and then go ahead and fill the burette with that titrant. And notice the dark purple color of the potassium permanganate solution. Then in the Erlenmeyer flask with your magnetic stir bar, you should put about 25 milliliters of deionized water. It doesn't have to be exact because we're going to be much more precise with our other measurements. The hydrogen peroxide, you can just, I would suggest buying a fresh bottle each year. It's very cheap. I just get it from the grocery store. But the hydrogen peroxide, you want to measure 1 milliliter of that. So this is really a micro scale titration. The 1 milliliter of hydrogen peroxide, you could use a graduated pipette. You could, if you have it, use like a micro pipetter. You could use a volumetric pipette if you have one for 1 milliliter, but try to get that 1 milliliter as close as you can. And that goes into your Erlenmeyer as well. And then because the solution needs to be acidified in order for it to work, you have to have those excess of hydrogen ions, you're going to use sulfuric acid. And this is a very concentrated strong acid, 6 molar sulfuric acid. So be really careful. Typically I would do this in a fume hood, but since there's no students around, I'm going to go ahead and do it out here with gloves. So I'm going to measure out 5 milliliters of the sulfuric acid using the graduated cylinder. Again, if you have a volumetric pipette or even a graduated pipette, that would work as well. And it's okay if this one is not exactly 5 milliliters, as long as we have an excess of those hydrogen ions so that the reaction can proceed properly. Now I'm going to add the sulfuric acid into the water and hydrogen peroxide in the Erlenmeyer flask. This is another case of making sure that there's water in the flask to begin with before you add the strong acid, because that dissolution process is very exothermic. So having the extra water can help protect, basically, act as a safety measure for any of the heat that's released when the sulfuric acid dissolves. Now I'm going to place the Erlenmeyer flask on the hot plate stirrer, and I will turn the stir on very low. We don't want it too high so it doesn't splash. And we don't need an indicator for this. The reason for that is the purple color of the potassium permanganate. When that drips into our hydrogen peroxide and sulfuric acid, it will react and change that purple to colorless. And it will continue to do that until there's no more hydrogen peroxide or acid. In this case, hydrogen peroxide is our limiting. But it will continue to change it colorless until we use up the hydrogen peroxide. And then it will stay like a faint purple. So that's what we're looking for as our endpoint, is that faint purple color to persist. So that way we know that there's no more hydrogen peroxide able to neutralize the purple potassium permanganate. So now that you see the faint purple color remaining in the flask, we know that all of the hydrogen peroxide has reacted. You can even see a few bubbles of the oxygen gas that was produced forming on the side of the flask. But that means that your titration is finished, it's reached the end point. And also make sure that students notice that in order for the purple color to be seen in the flask, it must have gone just a little bit past the equivalence point, because there's a little bit of the potassium permanganate that did not react in your flask now. That's what gives us that purple color in the flask. So that is a source of error, that you used slightly more potassium permanganate than you really needed to reach that stoichiometric equivalency. So now that our titration is finished, we can calculate the concentration of hydrogen peroxide in the drugstore bottle that we tested. This was our titrant, the 0.02 molar potassium permanganate, the dark purple solution. It took 20 0.25 milliliters of the 0.02 molar potassium permanganate to fully titrate the 1 milliliter of hydrogen peroxide. Remember, there was also water and sulfuric acid in the flask, but that was there to help the reaction proceed, and those were in great excess. So for our calculations here, the first thing I want to do is take the molarity of the MnO4 times the liters, 0.02025 liters. Molarity times liters gives us moles. And then once I have the moles, I can use the mole ratio from the balanced chemical equation. In our balanced equation, there were 2 MnO4 for every 5 H2O2 that reacted. So our 1 milliliter of hydrogen peroxide had 0.00101 moles of hydrogen peroxide. And so to find the concentration, I need to divide by the liters. Since it was just 1 milliliter, that's 0.001 liters. And so when you calculate that, you get 1.01 molar H2O2 as our experimental concentration in the drugstore bottle. Now, if the label is correct, it was 3% hydrogen peroxide, that corresponds to 0.882 molar because it's 3 grams for every 100 milliliters. So this is the concentration you get. You can calculate the percent error, especially if it's a fresh bottle. If it's a really low bottle, it's probably going to be much lower because hydrogen peroxide decomposes naturally over time. So experimental minus the theoretical, all over the theoretical, times 100, and we got a 14.8% error. So why would we have wound up with a higher concentration than expected? Well, it's most likely because we titrated a little bit too far. So we added additional potassium permanganate than what was needed. So we had a larger volume. Because there was a larger volume, there's a larger number of moles calculated. So a larger number of moles of hydrogen peroxide, and therefore a larger molarity. Always make sure to walk through the error all the way to your final answer to see how the error would have affected your final result.